So we will now go over an example with a solution, and afterwards we will be solving 5 more examples to make sure we understand the normal distribution, which is a continuous type of random variable distribution, right? Previously we looked into the binomial distribution and similar discrete random variables and their distributions. Normal distribution is a distribution for a continuous random variable, so that's important. Examples of continuous random variables, distributions for continuous random variables include the uniform distribution as well as the normal distribution. These are the two most popular distribution. Obviously there's tons of them, right? So like the chi-square distribution, you name it, the exponential distribution, gamma distribution, beta distribution, and so on. For discrete random variables, the main example is always the binomial distribution. Okay, so now for this one. So here is the example and the solution underneath and a picture as well. We want to make sure we understand all this. So the achievement scores for a college entrance examination are normally distributed with a mean of 75 and a standard deviation of 10. So this is one of the key ideas behind normal distribution. So normally distributed, so we know we have a normal distribution, but normal distribution has two parameters that we need to enter into the formulas, the mean and the standard deviation. Once you know the mean and the standard deviation of the normal distribution, you can make any calculation you want. What fraction of the scores lies between 80 and 90? Well, you guys can see the picture here. Let me provide you two different ways to solve this problem. The first method is to standardize it. Usually that's not the way I solve the problem, but I will show you the solution anyways. And then the second way, because we are using Excel can do a really good job. We don't have to standardize. We can directly solve the problem as it is. All right. So this one, the first solution is with standardization, So how do we standardize? We standardize using this formula. So here y is the random variable of interest in this example, achievement scores for this college entrance examination. So we are told that, let me write it again, we are told that y is distributed normally with a mean of 75 and a standard deviation of 10. So our goal is to standardize this. By standardizing, we are going to convert this into a new, into a new random variable, right? So let me make it slightly smaller so it fits the screen. There we go. So this is how it was. So we are going to turn it into a standard normal distributed normally, but with mean 0 and standard deviation 1. So that's the whole point. So when you apply this transformation here, this function, it will turn this into a standard normal. All right, so this is the old school way of solving these problems. I'm just going to do it anyways, because most textbooks, they have a standard normal distribution table at the back of the book. They used to show this a lot in the past, but today, because we are using Excel, this is kind of old-fashioned. We directly solve the problem. But anyhow, regardless, let's just do it. So all I need here in this formula is to plug in, because the question is asking for the probability, the fraction of the scores which will lie between 80 and 90, somewhat above the mean, right? Between 80 and 90, it's asking for a range. So we calculate the standard normal for 80. 80 minus mu is the mean, sigma is the standard deviation. So 80 minus 75 over 10, 0.5. 90 minus 75 over 10, 1.5. So this is the range, 80 to 90, right? I want to calculate the probability. Let me write the question. The question is asking for the probability that our random variable y is between 80 less than or equal to y less than or equal to 90. So that's what the question is asking for, right? But what we are doing effectively is, by standardizing it, we are turning this problem into the following problem. All right, make sure you understand the distinction. The probability that now that we have this transformation, y is transformed into a z, right? So we want the z, because now we found those two values, we want z to be between 0.5 less than or equal to z less than or equal to 1.5. That's it. That's not a new problem. All right. And that's it. So now we want to find, so when you plot all this, the normal distribution is a Gaussian distribution, also known as the Gaussian or the bell curve. So this is the bell curve. So the normal distribution, the original y variable, also had the same picture shape, except what I did during the transformation, when I applied this transformation, I shifted it by mu and divided by sigma. I basically translated the whole picture onto a situation where, so this is z, right? So this is the probability distribution for z, where the mean here, the vertical symmetry line here is at 0. You can't see it here, but that's at 0, right? And yeah, so you want to find the area between 0.5 and 1.5. You know that the area underneath the whole distribution is a 100%. So the area between 0.5 and 1.5, this dashed area, that's what. So when you eyeball it, it seems like close to 1/3 or 1/4. And sure enough, when you solve the problem, it's 1/4. So how did we solve it? Well, the fastest way to do it is using cumulative distributions. Find the area to the, oh, there's a typo here. It's the other way around. My bad. Oh, no. I think, oh yeah, I see what's this is not the cumulative distribution. So what they are doing is this formula provides you the area for the random variable to the right of the random variable. So if you want to find the area to the right of 0.5, that's the whole thing. And then the area, if you subtract from that the area to the right of 1.5, that will give you the answer. I wouldn't have done it this way. I would have rather done it to the left. So the area to the left of 1.5, this whole area, subtract from it the area to the left of 0.5, that will give you the dashed area. Right, so let's do it that way using Excel. So Excel has this super cool formula called norm S dist. Norm S dist. So Z is 1.5, and you want cumulative true. From that, we want to subtract norm S dist 0.5 basically, because it's already standardized and this is true as well. And boom, that gives you the same probability. So the desired probability is equal to 0.24173. Yeah, that's the same. So 24% roughly. Does that make sense? So here we use the norm dist, so norm z dist. So this is standard normal distribution. So we converted our original normal distribution with a mean 75, standard deviation 10 into a new random variable with mean 0, standard deviation 1, and that's how we solved it. Standard normal distribution. And the function for that, let me remind you, norm S dist, right? So that's the, oops, how did I do it? Z cumulative. Let me just write it out. There you go. I want to show the whole formula. Okay, there you go. Alternatively, we didn't have to do all this translation. We could have kept the normal distribution as it is with a mean at 75 and standard deviation 10. We could have directly solved it. So let's solve the problem direct solution. Direct solution using norm dot dist. But oops, sorry for that. Norm dot dist. When you do that, norm dot dist will ask for a couple of different standard deviation and then whether true or false, which we will use cumulative again. True. Yeah, it will ask for quite a few parameters, so that's the downside. Either you do the calculations ahead of time and then it's easy. All you do is, if you want to see that formula again, it's just plug in the z value and then write true. Very easy. In this case, it will take us 2 steps. So the probability, so we are calculating this probability here, Control Z. Oh, sorry, I meant to say Control C. Yeah. All right, let's get rid of that. Okay, so the way we will do it is, we will actually, let me write how I'm doing it, going to do it. We're going to find the probability that y is less than or equal to, oops, less than or equal to 90. And from that, I will subtract the probability that y is less than or equal to 80. The difference will give us the answer, right? So equal to, let's do it, norm dist, not norm S dist. It's not standard anymore. I'm going to ignore all this solution. I'm going to, by just the givens, I'm directly solving the question. What is the x? X is 90, or the y? Y is 90. What's the mean of the distribution? 75. What's the standard deviation of the distribution? 10. And then we will say true. So it will give us the area to the left of 90, minus from that subtract norm dist, again 80 to the left of 80, the area to the left of 80, 75, 10, true. That's it. That gives us the same answer. So you guys can see that either way we got the correct answer. 24.17% is the fraction. So 24% of the scores are expected to be between 80 and 90. Awesome. So like I said, I will not do it like this. Most questions I will directly solve it using this alternative solution, using the norm.dist function, unless the question is directly given to me as a standard normal. It's never given as standard normal, almost never. So we will always, but it's good to know the logic behind the standard normal. The normal distribution also have a bell curve shape like this. And because Excel is so powerful, we are directly using norm.dist function, this function, to solve all these problems. All right, so let's go ahead and solve 5 examples today. Here's the first, well, after that first example. Okay, here's the first example. Z represents, so whenever you see the letter Z, be aware that's standard normal. All right, so this is standard normal. So we want to make sure, standard normal is just a special case of a normal distribution, where the mean, let me write that down, mu, the mean is 0, and the standard deviation is 1. So it is standardized in that. Actually, let me just write it like this. All right, there you go. Otherwise it's confusing. There you go. So the mu is 0, standard deviation is 1. If you have such a distribution Z, what's the probability that Z will be between 0 and 1.2? What's the probability Z will be between, the random variable will be between minus 0.9 and 0, and so on? Well, that's very, very easy, right? So let's just go ahead and use we can directly even use norm.dist function. We don't even have to use norm.s.dist. I mean, in this question, obviously it will be faster. Let me solve it in 2 different ways. Norm.s.dist, very straightforward. What is the Z? 1.2. From that, with cumulative true, right, I want to subtract all the ones which is to the left of 0. Norm.s.dist again, to the left of 0, true again. Oops. So that would be one way to, by just using norm.s.dist function. Alternatively, or we could have used the following. So by the way, what did I do here? Control X. Let me just explain what I did here. What I did is to calculate the probability that, well, it's over here, right? It's the same thing. 0 less than or equal to my random variable, which we decided to call it Z. Doesn't matter. You can call it X or Z. Doesn't matter. Less than or equal to 1.2. That's what I did here. I hope that makes sense. Alternatively, we could have used directly the norm.dist function, even though it's a standard normal. So it's an overkill, but let's just do it. 1.2. The mean is 0. The standard deviation is 1. And cumulative is true. And from that, I want to subtract norm.dist again. The mean is 0. Sorry, the random, so the left side. So I want to subtract from those all that are random variable is 0 or less. 1.2 or less, subtract 0 or less, that will give you the range between 0 and 1.2. The mean is 1. Sorry, 0, I meant to say. The standard deviation is 1, and then again, this one is a true. All right, so that's the same answer. Okay, so part B. Now, I think it's very straightforward. The probability that it is between minus 0.9, less than or equal to Z, less than or equal to 0. There we go. So norm, you know what, I'm just going to well, okay, let's just do it 2 different ways again until you guys get familiar with that. So we want to find the area to the left of 0 and subtract the area to the left of minus 0.9, and that will give you the area between them. I think that makes sense already. 0 here, true gives you the what do you call it? The cumulative. Norm again, norm s.dist, between minus 0.9 and then again true. That's it. So that's the answer. Or let's write by just using the norm dist directly. So it would have been a bit longer, but we could have done the problem like that as well. So norm dist 0 to the left of the area to the left of 0, where the mean is 0, the standard deviation is 1, and then this is a true, minus norm dist the area to the left of minus 0.9, mean is 0, standard deviation is 1, true again, and boom, the same answer. All right, fine. Oops, what did I do here? Control Z. Last one. The probability that Z is between 0.3 less than or equal to Z less than or equal to. Notice that less than or equal to doesn't matter in continuous distributions, random variables. In the binomial, it was important whether it's less than or equal to. Here I'm gonna use a sloppy language. Sometimes I write less than, sometimes less than or equal to. It's the same thing. When it's continuous random variable like a normal distribution, it doesn't matter. All right, so okay, let's solve it in two different ways again. Equal to norm S dist. The Z is the area to the left of 1.56, true, because we want cumulative, minus the area to the left of 0.3, true. That's the answer. Or we could have used directly norm dist function. It will be a little bit more painful, but we'll do the same thing. The area to the left of 1.56, where the mean is 0, standard deviation is 1 and true, minus norm dist. The area to the left of 0.3, where the mean is 0, the standard deviation is 1, and true cumulative probability. It's the same answer, as you can see. 32.27%. All right, so we are done with the first question. The second question is asking for the values of the random variable themselves, right? So do you guys see that? It's asking for what value of Z is such that I will get a 0.5. Well, this one is obvious. It is because it's a symmetric distribution. Yeah, it has to be 0 itself. Why? Because half of the probability that the random variable Z is less than 0 is 50%, and more than 0 is 50%. Why? Because there's symmetry around 0, right? So the Z0 here will be 0. So that's the answer. 0 by symmetry. But let's just do calculations, I guess. So what we want is to use the norm, the inverse normal distribution. Let me show you. Norm.s.inv. So it's asking for the actual probability, 0.5. Now notice that this will give you the area to the left of. So because in this one it's asking to the right, we need to subtract 1 minus 0.5, right? Which is again 0.5. Does that make sense? 1 minus 0.5, which is 0.5. So yeah, but yeah, that's a 0, so that makes sense. Okay, you will more practice, you will get better at it. So let me just keep going. So for instance, this one is the correct. The area to the left of this number is 86%. What is that number? The area to the left of a number is okay. Do you want to use norm S dist or norm dist, right? So either way would have worked. Okay, let's solve this one in both ways. So norm dot S inv, the area to the left of that number that we want to find is 86.43%, right? You can either write 86.43% as a percent, or you can directly say 0.8643, right? So it's the same thing. So this will find the area to the left of that number is 86.43. What is that number? That number is 1.09. Or we could have used norm dist function. Let's just do it. Norm inv function, right? So the probability is that number, 0.8643. The mean is 0. The standard deviation is 1. That's it. It will give you the area to the left. Which number? The area to the left will give you 86. It's the same number. Perfect. And finally, part C. Oh, C and D. There's two more. There is a number, a range with that number. The range will be 90% within that interval, 90%. One way to do it is the following. I think it's a fancy way to do it, but it's a good way to do it. Because in this, because the standard normal distribution is symmetric, so what we can do is we can find the area to the left of say Z0, and hold on, the range is the area between minus Z0 and Z0 is 90%, which means in the tails we have still 10%. Half of it will be on the left tail, half of it will be on the right tail, so 5%. So that minus Z0 will be 5%, right? Does that make sense? So I can use this norm dot s inf. So the probability is 0.05. It will give me a negative number. I need to write the positive, report the positive one, because that's the minus Z0 that I'm going to get here. All right, so press, and there you go. So therefore, implying, or let's just write implying Z0 is actually equal to the positive of it. So which is, or you can just say equal to absolute value of this number. Does that make sense? So basically, what just to confirm the result, verify the result, just to verify that we did everything correctly. So we are saying that between this number and this number, the area between those two numbers is 90%. Let's check if it works. I'm going to confirm the result right here. So norm s inf. So the probability. Oh, sorry, norm s dist, I should say. What am I doing? So this will report the probability. I want the probability between these two numbers. To the left of this number, subtract to the left of this. That will give you the range between them. So this true minus norm dot s dot dist to the left of this number, true. There you go. And 90% it is. So perfect. Yeah, I hope that that clarifies. It might have been a little bit challenging, this exercise, but the key idea that I used is that the bell curve is symmetric, and the areas on the two tails, because of the symmetry, because those two numbers are symmetric, the areas on the two tails are equal. So if 90% is between those ranges between minus Z0 and plus Z0, so it means 5% should be on the left tail, 5% on the right tail. That's how I came up with this number, right? F2, 5% here. And then that will give me the area to the left of that number, which is 5%. So that number is this. All right, so finally D. So again, another number. So I think this one is straightforward, right? So we will just do the same thing. So the tail will have 1%, both tails. Half of it is half of 1%, which is 0.005, right? So norm dot s inf 0.005. So that will give me the left tail, implying Z0 itself is the absolute value of that number here. So we are farther from the mean. The mean was 0, right? We are farther from the mean. As a result, we can cover more area, 99% of the distribution. That makes sense. And we can easily verify the result. You guys go ahead and verify it. All right, now 3 problems in practice. How do you use all this? After all this abstraction, it's time to solve some actual problems. So 3 of them will really make us understand the logic. So the weekly amount of money spent on maintenance and repairs by a company was observed over a long period of time to be approximately normally distributed, with mean $400 and standard deviation 20. So we have a normal distribution here. Let's write that down. Our random variable is normally distributed. Normally. So that's the notation we use. X tilde norm n. That means normal distributed, with a mean 400 and standard deviation 20. What that means is X is normally distributed, mean with mean 400 and standard deviation 20. All right, that's the meaning. So all these words, that's the same thing as this notation. Distributed, so that tilde sign is distributed normally and so on. 400 mean, 20 standard. If $450 is budgeted for next week, what's the probability that the actual cost will exceed the budgeted amount, which means our budget will end up being violated? It's very likely we will remain within our budget because we know the normal distribution is symmetric. $400 is the mean, meaning there's a 50% chance the budget will not exceed 400, right? So how do I know that? Let me quickly check that. Norm dot dist, well, 400, the mean is 400, the standard deviation is 20, and then this one's a true, so this will be 50%. So this shows that the distribution is symmetric, right? So there's a 50% chance the budget will be 400 or less. The question is, what are the chances that we will be way over our budget, in a sense, $50 on our budget, $50 or more on our budget? Does that make sense? So really the question is asking for the following: the probability that x is greater than or equal to 4. Well, because greater than or equal to or greater than doesn't make any change, I'm just, from now on, it's annoying to skip writing that equal sign. So that's what the question is asking. So how do we answer the area to the right of a random number? Complementary counting. 1 minus the area to the left of that number. That's it. So that's exactly what I'm that's exactly what I'm going to do. 1 minus the probability to the left of 450. Does that make sense? So therefore the answer as a result will be norm dot dist, the area to the left of 450, given that the mean is 400, the standard deviation is 20, and this is true. Oh, sorry, I forgot the 1 minus. Oh gosh, I wrote it above it and then I forgot. Okay, there you go. So very, very unlikely, right? Well, the reason it's very, very unlikely because notice that the standard deviation being 20, 450 is how many standard deviations away from the mean? It's 2.5 standard deviation away from the mean, right? 2.5. So if you wanted to use standard normal distribution to solve the problem, 2.5 would have been our number, right? So for instance, let's solve the same number with standard norm s this. So it would have been norm, that's a 1 minus norm dot s does dist 2.5. Do you guys, oh sorry, I meant true here. Do you guys see why 2.5? Because if the standard deviation is 20, we are from 400, we are how many standard deviations away? 450 is 2.5 standard deviations away. The gap is 50. 50 divided by 20 is 2.5. And that's it. That should have given you the same answer. All right, so or. Awesome, so that solves that problem. Second problem. Okay, so a machining operation produces bearings with diameters that are normal distributed with mean this inches and standard deviation this inches. Now these are annoying numbers. All right, but let's just do it anyways. So the normally distributed with mean 3.0005 and standard deviation is 0.0010. All right, so these are quite annoying, meaning x is normally distributed with mean equals 3.0005. I hope I didn't add too many zeros here. And then standard deviation is 0.0010. All right, there you go. So then the question is, specifications require the bearings diameters to lie in the interval, in this interval. We want the interval to be this. So basically those outside the intervals are considered scrap and must be remachined. With the existing machine setting, what fraction of the total production will scrap? So basically we want to find the probability outside that range, right? So what is the desired probability then? Probability is what? Is equal to, we want to find the probability, so 1 minus basically 1 minus the probability which is outside that range, right? So which is 1 minus the probability inside that range. So that would be 3.000 minus 0.002 and then less than x less than 3.000 plus 0.002. Oh, well, okay, let's just write it like this, I guess. Let's put another 0 here. All right, so is everyone clear on what I did here? So the question is asking, we want to remain in this range, so that's the desirable range. We can calculate what is 3 minus that number. That's okay, it's not a big deal. Or similarly the plus. But because we want to figure out the problem cases is the one when we are outside this range, right? So that's what needs to be done. So let's just calculate the ranges, the lower range and the upper range. Lower bound. The lower bound is just that number, 3.000 minus 0.002. So that's the lower acceptable, and the upper acceptable one is, as long as we are within those two, we should be in good shape. The upper acceptable one is equal to 3.000 plus 0.002. So as long as the diameter of these cubes, I guess, whatever it is, are within this rate, we are okay, right? So basically, what we can do is we can find the probability to this or below, subtract the probability this or below. That will give you this range, after which I will subtract it from 1. So therefore, the answer, the probability, the desired probability of scrap and remachining, of scrap. All right, so that would be equal to 1 minus open parentheses. All right, so here we will have norm dist. So the number, the upper bound is this one. We want to find the left of this number, right? The mean is 3.0005, I guess. Yeah. The standard deviation is 0.0010, right? And then the cumulative is true. This is the left of that, minus norm dist. This time it's gonna be the lower bound. So the area, if I subtract the lower side left to the left of this number, subtract to the left of this number, that will give me the area between them. But I don't want to calculate the area between them. I want the area outside of them. So that's why I started with 1 minus. The mean is again the same number, 3.0005. And the standard deviation is 0.0010. And oops, I hope that's correct. Let me just write it like this. All right, so I close the parentheses for norm dist and then close the parentheses for that 1 minus thing, and that should give me the probability of scrap. So 7% chance, let me write it as a percentage, 7.30% chance we will be producing defective units that needs to be reproduced, I guess. Finally, last part, last question, example 5. Okay, so we did good today, I hope, with this video, I should say, lots of videos. The grade point averages of a large population of college students are approximately normally distributed with a mean, okay, so normal distribution X. So this is, X is the GPA, the GPAs of students, let X be. And we are told that X is normally distributed with mean 2.4. So the mean GPA in a school is 2.4 with standard deviation of 0.8, right? Then what? We'll possess a GPA. Okay, so we want the fraction. So the first part of the question, part A. What is the probability that the students will have a GPA in excess of 3.0? X is strictly greater than 3. It doesn't matter, strictly greater or greater or equal to, it doesn't change anything. So that's what the question is asking. Very easy. Norm dist, I guess, right? So X is, oh well, wait, because it says the area to the right, norm dist gives the area to the left if you use the cumulative feature. It gives the area to, it reports the area to the left. So I should have started with 1 minus, right? So 1 minus norm dist. So the X is a 3. The mean is 2.4, the standard deviation is 0.8, and true. That's it. That would be the answer. So 22.66% of the students will have a GPA in excess of 3.0. They will be like 22% of students are honor students if you want. Okay, so second part. If students possessing a GPA less than 1.9 are dropped from college, oh gosh, what percentage of the students will be dropped? Very tiny, I hope, not too many. It will be sad to see too many students. So the question is asking for the probability, which is for which x is strictly less than 1.9 basically. Hey, that's very straightforward. So it's just norm dot dist as usual, 1.9. The area to the left, that's perfect. X less than means the area to the left. 2.4 is the mean, standard deviation, and then true, the cumulative. Oh my goodness, 26% of the students will be dropped out. Finally, suppose that 3 students were randomly selected to represent the student body in some committee, I guess. And so what is the chances that all 3 of these students has a GPA in excess of 3.0? Well, pick 3 students, all 3. Wait, if I picked the probability of picking 1 student whose GPA is 3.0 or above is 22%. Randomly picking 3 students and all 3 having GPA in excess of 3.0 is very unlikely. It's the product of these 3 times, right? So the desired probability, all 3 students GPA greater than 3.0, well, that would simply be equal to the probability of a single student being great. Oh shoot, hold on. This is just equal to the probability of a single student being greater than 3.0, the first student, times the probability of the second student. You can call it x2 if you want. x2 is greater than 3.0 times the probability of the third student, x3, being greater than 3.0. Does that make sense? Let's write that. Oops. This is student 1. So we have student 1 greater than 3.0, student 2 greater than 3.0, student 3 greater than 3.0. That's what so that's just this probability times the same probability times the same probability. Extremely unlikely event. 1% chance. So if you're randomly picking 3 students, don't cross your fingers to expect that those 3 students will be successful students. It's very, very unlikely that all 3 of those students will be as successful as you might imagine. The chances that all 3 will be successful is only 1.16%. All right, so I will just stop this video here. Hopefully this was a good application introduction to normal distribution.